a look at some of these announcements. So homework 1 that we talked about in the last class period, I should put that on here. Homework 1 due Friday. That's tomorrow by 5 p.m. You need to upload it to MU Online. You can't submit that on paper. You can't just email it. It needs to be submitted electronically on MU Online. So that's due tomorrow by 5. And then the next assignment you have is due on Tuesday the 28th. So we're going to be going over a lot of material today to help you prepare for these problems on the homework assignment that's due Tuesday of next week. And that needs to be submitted at 11 o'clock. Although the deadline for this first assignment's at 5, all the rest of the semester your assignments need to be submitted before class. And that'll automatically close. That's not something that I'm going to go back in and change the timing of. You just need to be sure that you have it submitted before class starts. So any questions on the announcements? Okay, so today we're going to be talking about fluid viscosity and gas laws. Before we get into that, last time in class we were talking about the idea of density. And remember, we saw the density right before our eyes because we were calculating volumes and measuring the mass of a fluid, and density was the key variable that related those two factors together. What this figure shows, and it's taken from the appendix in your book, is that density of a liquid like water varies as a function of temperature. And water is most dense when it's cool, but as the water warms, the volume it occupies expands. So for a certain amount of water, you can see that the density decreases as temperature goes up. And that's not because there's less mass as you heat the fluid, but it's because the fluid occupies more space. So therefore, in these units, kilograms per cubic meter, for 1 kilogram of water, it's going to occupy 1 liter of volume down here in the low range. But at the upper range, as water begins to warm, then it's going to occupy more space. And of course, we all know that as water freezes, it expands a lot. And so that's why ice floats on top of water. Who can refresh our memory on what specific weight is? What is specific weight? Okay, unit weight and specific weight, you're right, those two terms are interchangeable. Do you remember what's the formula that relates specific weight, which is gamma, and density, which is rho? What's the formula that equates those two variables?
Gamma equals density times gravity.
What is it?
Gamma equals density times gravity, right?
Right. So gravity times density is gamma. So if you multiply, you'll notice here, density is 1,000 kilograms per cubic meter. If you multiply that density by 9.81 meters per second squared, then we get 9810, and now they've turned into newtons because a newton is a kilogram meter per second squared. So if you multiply meters per second squared, which is G, by kilograms per cubic meter, then we'll have newtons per cubic meter as the units for the unit weight. Unless I tell you a specific temperature in a problem statement, then the default assumption is that water has a density. Oh, that's the wrong variable there. That's kind of weird. That shouldn't be sigma. That should be rho. I'll fix that later. So the density of water is 1,000 kilograms per cubic meter. Now, we're going to talk about elasticity and volume change, and I previewed this just in the closing seconds of our lecture on Tuesday. The idea is that liquids are considered incompressible, but if we're more specific about it, they're very, very slightly compressible. And we can calculate the fractional change in volume by considering the bulk modulus of elasticity, which is a fluid mechanics property that describes how much pressure is required to cause a fractional change in volume. So the bulk modulus of elasticity of water is 2.2 times 10 to the 9th pascals. And we can rearrange this formula in our mind to think of it as some change in pressure causes a differential change in volume, or the density is going to be changing. If we compress the fluid, then the fluid is going to become more dense. So just as an illustration of how this formula fits together, let's consider this example that's mentioned on the bottom of the screen. If we start off with 50 liters of water that's open to the atmosphere and therefore just under standard atmospheric pressure, what would be its final volume if a pressure of 5 megapascals is applied? Okay, so for that, we're given this equation that we start off with, and I'm going to write that as E sub v is minus delta P times the starting volume and the change in volume, divided by the change in volume. Okay, now this minus sign, we need to think of, what is the meaning of that minus sign? And the way to interpret that is that if we have an increased pressure, then there's going to be a decrease in the volume occupied by the fluid. So the initial volume is 50 liters. And the bulk modulus of elasticity for water, E sub v, 2.2 times 10 to the 9th pascals. And then the delta P is 5 million pascals. So we're applying 5 megapascals. So the final volume is what we want to solve for. So let's first of all calculate the change in volume, and we can rearrange our bulk modulus formula to solve for delta V. Okay, so delta V is negative delta P times the initial starting volume divided by the bulk modulus E sub V. So I basically just algebraically rearranged this equation to solve for the change in volume. And now let's put the numbers in for that. So it's minus delta P. This marker is starting to go sideways. Let's see if I've got another one. Okay, so the pressure that we're going to put in for that is the minus 5 million pascals. And then the volume is 50 liters. And we divide that by the bulk modulus of elasticity, 2.2 times 10 to the 9th pascals. Now, the units that's going to come out of this expression is going to be in liters, because that's the initial volume that we put in. We could have also converted it from liters into cubic meters, but it's fine to just our change in volume to leave it in terms of the liters, since that's what we started with, was the liters volume. But the change here, if you put in the calculations, 5 million divided by 2.2 billion multiplied by 50 liters, that tells us that the change, you should get 0.114 liters. Anybody else get that same change in volume? So then the final is going to be the initial minus the change. So final volume is the 50 liters that we started with minus 0.114 liters. So it's 49.886 liters. So that tells you that water, it's not really incompressible, but it's certainly much, much less compressible than a gas is. We could have compressed a gas down to a tiny fraction of its initial starting volume with that much pressure.
Is there like a standard for what measuring we need to use? Like, is liter what it is, or can that interchange with milliliters or ounces? Or
Great question. Most of the problems that we're going to be solving this semester we'll do in cubic meters. But since the initial units were described in liters, then I think it's reasonable for us to put the final units in liters as well.
So if we're given something in milliliters, we can do that just the same when changing? Okay.
Right. Unless it specifically says in the problem statement what it wants the final answer to be in.
Something.
That's right. Was there another question as well? Yeah.
The negative up there, should we just not include that in our answer?
Yeah, good question. I guess what I should have done is carried that through here. So the delta is a decrease. And so that just tells us that the final volume is going to be less than the initial. So I guess I didn't show it like I should have in those units. So we're not ignoring it, but we're just saying that the final volume was less than the initial volume. Great point. I'm glad you caught that. Yes?
The slash through the V, is that just to point out that it is? Okay.
Yeah, so,
it wasn't specifically.
well, it means volume because we use V for a lot of different things. Sometimes we use it for velocity in fluid mechanics, like talking about the speed that a liquid or a gas is moving through a pipe. So, putting the slash through it is just kind of to distinguish between the other uses of the letter V. So that means volume. That's a great question. I'm glad you asked that. Thank you. I wish we were watching TV. Yeah, kind of. All right. Are there other questions? Boy, that's going to be hard. We're really going to have to focus. All right. Well, let's do watch TV. It's not going to be as loud as that, though. Anybody know what this is? What are we looking at a picture of here? Honey. How did you know it's honey? It's not labeled. What are the clues that that's honey? Okay, the color, first of all. Yeah, it's... Okay, viscosity. What do you mean?
The thickness.
The thickness, yeah. So this is a metal spoon, presumably, and they're pouring it out of the spoon, and you can kind of just get a sense from this photo. Even though it's not a video, it's a photo, you kind of get the sense that it's pouring slowly out of that spoon, right? It's sticking together. And it's not, honey is sticky, but viscosity is something separate from that. You can have a viscous fluid that isn't like also sticky. Like if you got it on your hands, a fluid doesn't have to be sticky to be viscous. Think of like motor oil. Motor oil, for instance, is more viscous than water. And although it's slippery, it's not tacky because it doesn't have sugar in it. These little air bubbles are also clues that it's got it's highly viscous. Because if this was just water, those air bubbles would rise to the surface, but they're trapped. They're entrained in the liquid. And so that's kind of another visual clue that what we've got here is a highly viscous substance. So let's watch this video clip. Oh, hold on. This is going to get me kicked off. I gotta do this. The glycerin was deforming very slowly when the container was tipped over. So the definition of strain, you've all taken mechanics before, solid mechanics. The definition of strain is the deformation of a physical body under the action of applied forces. So, for instance, if I had a metal ruler, normally I bring a metal ruler to this class, I forgot. If I was pushing a metal ruler on the ends, it would start to bow and deform. And the harder I push, the more it's going to deform. So that's an illustration of strain, is that deformation under the forces that are applied. So the stress is the force I apply, the strain is the response. In a solid, then the proportionality of the stress and the strain we call shear modulus. Hopefully that rings a bell. And one of the ways that we differentiate between solids and liquids is that in the case of a solid, it stops deforming when it reaches an equilibrium between the stress and the strain. But in a liquid, it's going to continue to deform as long as the stress is applied. Like if I had a tank of water and a propeller that's turning inside of that water, I'm going to be applying a stress, and it's going to keep deforming. It's not going to just deform one time and then stop deforming. As long as I apply a force, it's going to continue to deform. Now the proportionality factor in solids, instead of calling it shear modulus, in fluid mechanics, we call that the viscosity. Now specifically, sometimes it's called the absolute viscosity or the dynamic viscosity. And those three terms all mean the same thing. Whether a problem statement says dynamic viscosity or absolute viscosity, or if it just says only viscosity, it all means the same thing. It's talking about how much a fluid deforms under the application of a certain amount of force. So the stress and the strain. The strain is the response. The stress is the force that's applied. So this is a picture of a stream, and sometimes what we'll use the understanding of viscosity for is to characterize a velocity profile. In a river, let me draw just kind of like a cross-sectional view of a river, and we'll talk about how viscosity relates to that. So here's a river going downhill, and here's the water. The speed of the movement of the water isn't the same at every depth. It would be wrong if we assumed the water was all going the same speed at the top and at the bottom. More realistically, what's happening is that the water that's very close to the bottom is going slow, and it progressively increases in speed so that there is a velocity profile that looks like this shape. And part of that is because at the bottom of the river there's rocks and whatever the surface is made out of, whether it's rocks or clay or a smooth concrete surface, regardless of what the material is, it's applying a resistance force to the water in the opposite direction of the water's movement. And so the shape of that velocity profile is influenced by the viscosity of the fluid. So here is an image of that same velocity profile that I've drawn on the board here, but what it shows is a certain distance up from the bottom of a channel bed, and the velocity is increasing the further away you get from that surface of resistance. So the unmoving surface at the bottom, you can't have water slipping over without any frictional losses. So we call it, the phrase is the no-slip condition. The no-slip condition. So what the no-slip condition is that there has to be, the water will have the same velocity as the surface right at the interface between the two. The water actually has a velocity of 0. That molecule that's just above the water, the channel bottom surface, has the same velocity as the channel itself, which is motionless. But then the further away you get from that point of friction, the velocity increases. So we can think of that maybe as a river. Now, let's look at this video clip that illustrates, again, I think I better pause this. I got to keep remembering to turn that on. All right. So the terms that we're going to be using, the viscosity is the resistance to the flow, the V is the velocity, the distance up from the bottom, and now the rate of strain is the ratio of the slope of the line of this curve. So dV dy. Remember that dynamic viscosity, absolute viscosity, or just using the phrase viscosity by itself, those all mean the same thing, and we're using the variable mu for that, and it's the Newton seconds per meter squared is the units that we're going to use most often. If you go to the back of your book in the appendix, then it has those units for viscosity. And shear stress, the way that we can calculate the force that's applied is by normalizing that on a unit area basis. And it's the stress that causes strain, which is the deformation. And here is the formula that relates the viscosity of the fluid to the rate of strain and the shear stress that's applied. Now this is an important formula, but the next formula I'm going to show you is even more important, because what it does is it takes this shear stress and we calculate shear force by multiplying the area that the shear stress is applied over. So let me show you what I mean. Before we get to that, just think about, in terms of viscosity, it's easier to walk through air than it is to walk through water. But the question is why? Like if you've ever been in a swimming pool, you know that you can't walk through the water in the pool as quickly as you can walk through air. And anyone want to venture a guess why that is?
The water provides resistance to you.
Good. So the water provides resistance. But why does it provide resistance? What's happening? Like think about your leg and the fluid.
You're displacing the water.
Okay? So right now I'm displacing the air. Like as I move through the air, it's getting out of my way. It's deforming. But if I'm walking through water, it also has to move out of the way, but there's more resistance to the force that I'm applying. So what we can say is that there's less friction in air, and the rate of deformation is greater than the rate of deformation for water. So air moves out of your way at a quick rate when you apply a certain shear force, and we don't have unlimited strength to push the water out of the way at the same speed that we normally walk through air. So we could graph that, actually. We could graph for a certain shear stress that you're applying. Think of that as a force. The amount of force that you're applying to the air, there's a lot of deformation for a certain shear stress. There's lots of deformation for air, and very little deformation for water, and even less for oil, for that same amount of shear stress that is applied. Now, viscosity is what we're saying is it's the slope of this line. For the amount of shear stress that's applied, how much deformation was there. And so this is saying A is the rise, which is the shear stress. B, which is the run on that slope, it's du dy. And du dy is deformation. Or in other words, back to that curve on the previous slide, du dy is, we could do a graph of this velocity distribution. And du is the change in velocity. dy is the distance away from some boundary. And we're going to use this. We're going to say, what is the velocity of the fluid? What is the difference between the distance between two surfaces? And we're going to use it to calculate forces. Okay, so think of velocity in two ways. You can think of it as graphically, it's the slope of this line where you're graphing shear stress versus the rate of strain. Or you can think of it as the ratio or the proportionality factor that ties in this equation the two variables together. So this viscosity relates shear stress and rate of strain. There is one other phrase that you need to be aware of. I already told you that absolute viscosity is the same thing as dynamic viscosity, and sometimes we just say viscosity. Those three things they're equal. Kinematic viscosity is different. Kinematic viscosity is used sometimes because a lot of formulas have both density and viscosity in them. And those formulas that have both of those variables, we might as well combine it into a single factor, especially because sometimes viscosity is related to density. And so to simplify that, the kinematic viscosity is the absolute viscosity divided by density. So here's the formula for kinematic viscosity, and you can go to the table in the back of the book and look up the kinematic viscosity for water, air, and other fluids at a variety of temperatures. And the units, if you see how the units cancel out, the dynamic viscosity was going to be Newton seconds per meter squared. Of course, we already know that kilogram per cubic meter is the units for density. And so since a Newton is a kilogram meter per second squared, if we were going to expand out that Newton into its base units, where all units are essentially made up of mass, length, and time. Those are the only three base variables that all other units are constructed from. So if we expanded out the newtons into kilogram meter per second squared up in the denominator and then canceled out everything that is like, then the kinematic viscosity is units of meters seconds per square. I'm sorry, meters squared per second. So just to clarify, these three terms are all viscosity, but kinematic viscosity is different, and we get it by dividing absolute viscosity by density. Okay, so shear force is shear stress multiplied by area. So therefore, that means if we know that shear stress, tau, is going to be the viscosity times the rate of strain, then we can get the shear force by multiplying the shear stress by the area that the shear stress is applied over. And so this all works out. If we're a stickler for the units, and we should be, then the units of force are newtons, and we get those units by having a shear stress multiplied by an area. du is going to be meters per second because u is a velocity. dy is an incremental distance, so it's going to be units of meters, and so all of that cancels out into units of newtons. Now this formula is really important for the homework that you're going to be solving, and so if we take a look at how to apply it, what we often do is just simplify this rate of strain term to be velocity over distance. And let me show you what I mean by that. We can do that when we assume a linear velocity distribution. And so let's say that we have a tank full of that liquid from the video, the glycerin. Glycerin was the one where it was shaken, it hardly moved at all. When it was inverted, it poured out really quickly. That was the glycerin. So if we had a tank of a viscous fluid and we're going to drag a plate through that tank, let's say it's a metal plate with dimensions of 3 meters by 2 meters. So I'm not sure which dimension we're seeing here. I guess this is the side view, and so it's probably, let's say, oriented like this. It is 3 meters long, 2 meters wide, and we're going to be pulling it through a fluid. Now when we pull it through the fluid, remember the no slip condition means that the fluid is going to be holding on to that solid surface. And so even when we apply a force, it's going to be moving slowly because the fluid particles have to deform in order for this to move. So we know the area of the plate, we know the viscosity of the glycerin that it's being towed through, and we know the velocity that we hope to achieve, velocity of 0.58 meters per second. Now, these distances from the top of the tank and the bottom of the tank are going to be important for us because we're going to calculate the overall net force. But the way it works is that there's a force on the top and also on the bottom of the plate. And so we have this tank, and it's Here's the plate that's being towed. So the distance to the top of the plate is 1.2 meters, and the distance to the bottom is 2.4 meters. We're going to calculate the force, the shear force on the top and the shear force on the bottom, and substituting it into this formula that we're given, which is area times viscosity times the incremental velocity. So I'm going to say delta V divided by delta Y. All right, and the bottom is the same formula. The difference between the two being that the distances, the delta Y, is going to be different from the top and the bottom. Okay, so for the top, the area that we're using is 3 meters by 2 meters. Okay, the viscosity of the glycerin we're given is 0.15 Newton seconds per meter squared. Newton seconds per meter squared. And the dV is 0.58 meters per second. And the dy, so from the plate to the top of the tank is a distance of 1.2 meters. And we can do that same approach for the bottom. So there's 6 square meters of surface area on the bottom of that plate. It's still being towed through the same fluid of 0.15 Newton seconds per meter squared viscosity. And then the incremental velocity is 5.8 meters per second. And the distance is 2.4 meters. So calculate those two forces. If you've got your calculator here today, and I hope you do, let's find out what is the force on the top plate, the force on the bottom plate, and therefore, what is the total force that we have to apply in order to move that plate through the fluid.
This is more like a conceptual thing, but could that force be applied anywhere on the top of the tank?
We're not applying it onto the tank. It's the force required to get the plate to move. So what we're calculating is, we're pulling this way on the plate, but then what the fluid is doing is the fluid is pushing like this way to resist that movement. And so it's really about the fluid is deforming, and that's where the force comes from. So the place we're applying the force is, we assume there's maybe like a string of some sort on the leading edge of that plate as it's being pulled through the fluid. Yeah, so the forces on the top of the plate are higher because the distance between the plate and the next surface is less. On your homework, you're going to be solving problems similar to this using this formula where you've got a cylinder. Let's talk about the key ideas of one of these homework problems. This is problem 37, and so if we go back to the announcement slide, it's the second to last problem on this set that's due Tuesday. Okay, so problem 37 is a problem that's related to viscosity and distances and falling surfaces. And so the problem statement says derive a formula for a steady rate of descent. I wanted to translate that for you first of all. You don't really need to derive something. I mean, this isn't calculus class. We're not going to be doing proofs and derivations and so on. What it's really asking is find the velocity when this is falling in equilibrium. So basically what's happening is we have this pipe, which is kind of like a hollow shell, and a solid cylinder is falling downward through that hollow shell. And what we know is the weight of the cylinder. So that cylinder weight is given as 15 newtons. We know the outside diameter, so that the pipe has a diameter of 100.5 meters, and the diameter of the cylinder is 100 meters. And so if we're going to do like a different cross-sectional view, here's the pipe, and here's the cylinder, and we assume that it's falling down the center, like it's centered in there. And so if we're going to draw the dimensions on this, it's 100 millimeters here, and it's 100.5 millimeters is this distance. So there is, in the gap between the cylinder and the pipe, it's lubricated with oil, with SAE 20 weight oil. The viscosity that I'd like you to use for this problem, you could find it on a table, but just so that we're all on the same page and you don't do your calculations with a slightly wrong viscosity value, use 0.35 newton seconds per meter squared. They also have told you the length of the cylinder, and in a minute we'll talk about why they've defined that. What you have to do here is a force balance. What does equilibrium mean? This word equilibrium. Okay, balance. It means balance. If it happens on one side, it happens on the other. Here, what it means is that it's reached a terminal velocity, that it's not changing its speed, and the forces are all balanced out. So in equilibrium, the forces are equal. The forces down and the forces up are equal. So there's a shear force, and if this cylinder is falling downward, the shear forces that are applied by the oil to the surface of the cylinder, the oil shear forces are up, and they're all around. It's not that it's just on the right side like I've drawn it here. You know, the shear forces act over the entirety of the surface that's in contact with the oil. And so the applicable surface area in this case, you have to calculate the outside area of that cylinder. How can you know what is the area of a cylinder? It's not, just as a hint by the way, it's not pi d squared divided by 4. This is a formula for area, but this formula would tell you the area of the top of the cylinder. That's not what's in contact with the oil. That's not like the critical surface. The critical surface is the outside area of the cylinder. So what formula do we use for the outside area of a cylinder?
How do we find that the line in between?
You use the circumference, right?
Circumference and the height. Yeah, so think of it, here's a cylinder. I'm going to turn this piece of paper into a cylinder. Okay, so I want to know what's the outside area of this cylinder. So it's the circumference length multiplied by the height. So if I cut that cylinder and spread it out, what's the area of that? It's the top distance and the height distance. So circumference is pi d. That's circumference. And you multiply that by the height, which we're calling L, and that gives you the area of the cylinder.
Do we not need to add the area for the top and bottom of it?
In this case, we don't. And the reason why is, remember that the gap distance has a huge effect on the force. And so back to this other example, remember that the smaller the distance, the greater the force. And the top force was, well, let's see, where is it? If I go back to my numbers on that. In this one, the top force was 0.35, the bottom force was 0.21, and that was a gap of 1.2 meters and 2.4 meters. The reason why we're not going to account for the top and the bottom area of this cylinder is that it's this tiny little gap area that's kind of the critical distance that causes the vast majority of the forces. And by the way, we're going to substitute that in as a dy. And here's our formula that we're going to be using, dy. What's the distance? What's the gap distance?
0.25 on both sides.
Okay, so our first reflex is to say, oh, it's 0.5, right? But why is it not 0.5? Why is it 0.25?
Because there's opening on both sides.
Right, it's because on either side, this half a millimeter of clearance, it's split equally on the left and on the right. So this cylinder is falling down the center line of the pipe. So the dy distance that you're going to be using for this problem is 0.25 millimeters. And you'll need to convert it to meters for everything else to work out, since your viscosity and your area also are going to need to be calculated in meters. Okay, so we've talked about the critical area, and we've talked about the gap distance. The last thing that we need to talk about is that this is a force balance. So equilibrium says that the force down and the force up are equal. So force down is what?
Equals force up.
Force up. So how do we calculate what or know what the force down is?
Gravity.
It's due to gravity. So that cylinder weight of 15 meters. So, I'm sorry, 15 newtons. 15 newtons is the force down, and since it's moving downward, steady rate of descent, the force is going to be resisting, the shear force is going to be resisting that downward movement in the upward direction. So here is the shear force. It's up, and here's the formula for shear force. So what we're going to have to do is we're going to have to find equilibrium velocity. We know the area, it's given, it's the outside area of the cylinder. We know the fluid viscosity, it's given, it's constant. We know the gap distance dy. So the only thing that isn't defined in this expression is the du, which means the velocity, the rate of descent. So that's what you're going to be solving for in this problem 237. We won't go over every homework problem like this, but occasionally there are a few that I think would be helpful if I can translate what it's asking for, or maybe give you just a couple of hints and key ideas to get you started.
In this example, if the gap distance from the cylinder to the outside pipe was equal to or greater than like the distance that it was falling, would we take account of the area including the top and the bottom?
Well, it would depend where the oil is, because the problem statement could have said this is just a film on the outside and it's not actually falling, like it's not fully enclosed in oil.
Mm-hmm.
So the answer is it depends. Here in the drawing where it says oil film, that's their way of saying that actually the oil is not even in contact with the top surface and the bottom surface. It's just lubricating the outside in the same way that an engine's cylinder would be lubricated as the piston goes up and down.
So if it was submerged, then we would take the area of the top and bottom.
If it was submerged, then this problem would be different, and we wouldn't be able to solve it until we get to chapter 5. Yeah. Okay, so any other questions on this problem? All right, so another reason I occasionally hand out these breadcrumbs of key ideas is as an encouragement for you to start your homework as early as possible, because these hints are fresh in your mind right now. They won't be fresh in your mind Monday morning, or Monday night or Tuesday morning next week. So, you know, if you solve this one now, it's going to take you way less time than if you delay and procrastinate. Okay, so some other things about viscosity that we're going to address is that viscosity as a property is independent of pressure. So that means that the viscosity at the bottom of the ocean is the same as it is at the top of the ocean, that the pressure being experienced by the fluid doesn't affect its viscosity. And what causes viscosity is molecular cohesive forces. So in a liquid, as you warm up a liquid, what happens is that the fluid becomes less viscous because the molecules are moving around more quickly, and then that decreases their cohesive forces. But ironically, in the case of a gas, viscosity for a gas increases with temperature. So gases become more viscous as they're heated up, not less viscous. Who here has changed their own oil before? Almost all of us. All right, great. So you know that the oil pan empties a lot more quickly if you warm up the engine first. Because, you know, the reason you do that is by warming up the engine and warming up the oil, the viscosity decreases when it's warmer, and then it flows more quickly out of the engine. So in the case of a gas, what that means is that actually if you have more gas, because the molecules are bumping into each other, they have a lot more collisions, and the velocity of those collisions is higher. The gases are kind of getting in the way slightly more, and so the viscosity and viscous resistance is greater as the temperature goes up. Another thing that you need to know for the homework assignment is Sutherland's equation. Sutherland's equation is a way to estimate the variation of gas viscosity. Sometimes you can just look up out of a table the viscosity for a certain temperature that you want, but then there will be other times where you don't have a table available, and so what you can do is you can use this equation to estimate the viscosity at other temperatures. So Sutherland's equation would be used, for example, on a question like this. The viscosity of air is 1.95 times 10 to the minus 5th Newton seconds per meter squared at 50 Celsius. So what is it at 95 Celsius? So in this formula, the viscosity at the original temperature is this one. The temperature at that given temperature is put in, and we have to solve these in Kelvin, because remember what I said in the previous class, for most of our gas-related problems we have to use an absolute temperature scale. So although the temperatures in this example are given in Celsius, the first step is to convert to Kelvin, and another hint that you need to do that is that Sutherland's constant is itself in terms of Kelvin. So if you're going to be adding S to the given and desired temperature, the temperatures have to be in the same scale to be able to add them together. So I'm going to pause the recording and stop talking for a second, and what I'd like you to do is try and determine what is the viscosity of air at 95 Celsius. And remember that the conversion is you have to add 273 to get kelvins from Celsius. Okay, so remember that the purpose of this equation is to estimate viscosity of a gas at some temperature where you don't have the value known from a table. So you have to start with the value where you do know the viscosity, and in this case we know the viscosity at 50. So what we're saying is the original viscosity at 50 was 1.95 times 10 to the minus fifth Newton seconds per meter squared. And then we multiplied that by the ratio of the temperatures to the 3 halves power, where we've converted the temperatures to the absolute scale. Technically, it's 273.16 is the Kelvin version of 0 Celsius. So to convert between Kelvin and degrees Celsius, we add 273.16. So we know the initial temperature, we know the temperature that we desire to know the viscosity at, in this case 95 degrees Celsius. And then we also have this term where we add in Sutherland's constant, 111 Kelvin. So did anybody else get 2.15 times 10 to the minus fifth Newton seconds per meter squared? Okay, good. You'll notice that when I do these examples, I include the units. And I'm going to do that for every example we work through the entire semester and next semester when you have me for hydraulic engineering. I'm always going to include the units because, number one, it's easier to avoid mistakes if you write the units. Like, let's say, for instance, that I had forgotten to convert from Celsius to Kelvin. If I wrote the temperature in Celsius, then I'd right away see, oh, I can't add that Celsius to something that's in Kelvin. So if you include the units, one advantage of doing that is that it helps you to prevent errors. And then the other advantage is that by canceling out the units and making sure that everything's dimensionally consistent, you can ensure that you use the right formula in the way that it was intended. The other thing I'll mention about this solution is that I have intermediate steps. Like, it's really easy when you're putting things into your calculator to kind of lose the broader perspective. So rather than do everything just in one calculation and get the final answer, what I did was I solved, all right, what's the answer of inside of these brackets? Like the 368.16 divided by 323.16. That's 1.139. So I just did like part of the problem in one step. Same thing here. I found the result of that addition and ratio. And then as the final thing, I did the multiplication and the power step. And by having it kind of showing your work step by step, then you can double check it more easily. Like, I can just verify that I had the right answer by doing these intermediate steps and making sure that I get the same values that I did the first time. Any questions about this example using Sutherland's equation? So Sutherland's equation is used because gas viscosity varies as a function of temperature. Let's look at that temperature variation. What we already know is that oil becomes less viscous as it heats up. What I told you just a moment ago was that air becomes more viscous as it heats up. The trend is fairly flat. It doesn't become hugely more viscous, but it does come a little bit more viscous. So that's kind of an interesting point of fact that the viscosity increases. When we're talking about fluid properties, one of the things that we have to be aware of is the difference between Newtonian and non-Newtonian fluids, and this ties into viscosity. Let's start by just looking at a video clip that illustrates a non-Newtonian fluid. A non-Newtonian fluid is something where the viscosity actually responds to the shear force that's being applied. So the kid who's walking quickly, as he's jumping up and down on that fluid, the viscosity immediately under his feet is very high. It's viscous because a big shear force is being applied. But then this kid who wasn't moving very quickly, he was applying a low shear force, and so the fluid's viscosity was lower, making his foot able to sink down into the fluid because it was deforming easily. So let's look at this graphically. what we were just seeing was a shear thickening fluid. Most fluids like water is a Newtonian fluid. So in the case of water, its viscosity is independent of the force that's applied. It has the same viscosity whether you're applying a little bit of force or a lot of force. But in these non-Newtonian fluids, like a shear thickening fluid, which we just saw, if you apply a big shear stress, then the shear strain becomes greater. There are shear thinning fluids like toothpaste or ketchup is an example of a shear thinning fluid. And in a shear thinning fluid, it starts out with a lot of viscosity, but the more shear stress you apply, it becomes less viscous. And that's partly why in the case of a glass bottle of ketchup, you may know that you'd have to really hit the back of the ketchup bottle so much. Well, what you're doing when you apply that force to the back of the ketchup bottle, you're actually decreasing the viscosity of the fluid temporarily. So it can flow, and then it stops when there's no more shear force, and then you apply another bang to the back of the ketchup bottle, and the viscosity temporarily decreases. And so the fluid, in essence, is responding to the force that's applied. Let's look at this other clip. Okay, one last thing in the minutes that are remaining here. I want to show you the equation for how to use the ideal gas law for solving problems. PV equals nRT is probably something that you remember from chemistry class. But if we take the molecular weight of the gas into account, then we can solve problems using this formula here. If you've printed the notes, highlight this one, because this is the one that you need to solve problems like the example that I'll show you in just a second, which is also related to a homework problem you've got. What this says is that the pressure of a gas is equal to the density of the gas, R, which is the universal gas law constant. In this case, it's specific for the gas in question. And T is the temperature. Remember, you have to have temperature in kelvins when you're working with gases. So the example that I want to show you, I'll just put this solution on the screen here, and then if it would be helpful for you to work through it on your own time, you'll be able to do that by going back to the video recording. What we were going to do is we were going to determine the density, specific gravity, and mass of air in a room that's a 4 by 5 by 6 size. And so we've got a certain volume of air, and we want to know what's the density, the specific gravity, and mass. So the key to this is calculating the density first. The density relates to the pressure. And so in this room it says the pressure is 100 kilopascals. And so you put in 100 kilopascals. The R value comes from table A2. And then the T is the temperature of the gas, which you've converted from Celsius to Kelvin. So let me put here on the screen how you'd calculate, first of all, given all of these information that you'd convert from Celsius to Kelvin. Here's the R value, and just for fun, I show you what are the units if you break that down from joules per kilogram Kelvin into its base units. So you can calculate using that formula for density, the density of the gas. And then once you know the density, remember the definition of specific gravity is just the density of something relative to water. So here's the specific gravity. And then you could also calculate the mass of air in the room by multiplying it by the room's volume. Okay, we're out of time for today. It's 12:15, so I'll just switch back to these slides that have the announcements real quick to refresh your memory about what's due on Friday, tomorrow, the introductory assignment, and then Tuesday, these problem-solving questions. So I hope you have a good one, and I'll see you on Tuesday.
Yeah.